And welcome back to another LeetCode video. We just completed course schedule 2 in the section of graph problems. The graph valid tree is unfortunately LeetCode Premium, so I don't have access to that. But I can access the number of connected components in an undirected graph. So I wanted to have a look at this one next. And it sounds quite easy, so I'm pretty sure that I can just one-shot this. I have solved this before. And but that's 2 years ago. So yeah, let's just try this. That's LeetCode 323, number of connected components in an undirected graph. We are given a graph of n nodes, and you are given an integer n and an array edges, where edge at position I means that there's an edge between the first and the second element in the edge array. Cool. Return the number of connected components in the graph. All right, as the constraints. Okay, the number of, the edges are denoted between 0 and n. There's never a self edge, and we have at least one edge, meaning at least one node. Oh, no, at least two nodes, I guess. If you have an edge, we also have two nodes, at least, right? That's what that means. Cool. So, yeah, this should remind you a lot of, connected islands problem, I suppose, except now we're not dealing with the grid, we're just dealing with the graph structure. So it's not connected islands, the count number of islands problem. Number of islands problem. I think this is very similar. And yeah, so I'm quite confident that we should be able to solve it. So what is a component? Well, a component in a graph is a connected subgraph, basically. So while this whole thing is the graph, this is not connected. This graph is not connected, as you can see. So, how can we do this? Let's just take this example, maybe even take the two examples, and let's see. So what we have here is, we know how many nodes we have, right? And we are also giving n in our function here. So what we can do is, we could just say, I know what all the nodes are. So I'm gonna try to start to find all connected edges. So maybe in a for loop. So we're going to iterate with, maybe the node goes from 0 to n minus 1, right? And we're going to start to explore from node 0, try to find, all the nodes that we can visit by starting here. So we can go here, we can go here. So all nodes 0, 1, and 2, we mark them as reachable from that component, from that start. And once we run out of nodes to visit from there, we know we've explored one component, and we continue to iterate with n over our number of nodes. And we're going to run into a node that we have not visited yet. For example, node 3. So we haven't visited that one. That means, okay, now exploration starts again. We can also visit node 4. So in the end, and then finally, we have no more nodes left that are unvisited. And then our count is just 2. We've identified 2 components. And here, we would just start to explore from that node, and we'd be able to reach all of the nodes in the grid. And that therefore, we don't have to do anything anymore. We visited everything. So this seems rather straightforward. Now we're giving this graph as a set of edges. So what we will have to do is, we will have to create like a graph object so that we can easily traverse it. And we can do this quite handily. So if we just take this as, those are the edges. Since the graph is not directed, it doesn't matter. But what we will have, for example, what edge is connected to the node 1? Well, that is a list of connected nodes, and in this case, it's only the one. If we look at this node down here, we would have a graph, and for the node number 2, the list of connected other nodes would be 1 and 3. So that is how we can encode the graph structure. And when we start to explore from a certain node, we can use like a depth first search or breadth first search approach to continue iterating through all of the child nodes. So we start from one node, Then we start to iterate over all of the children, etc., etc. So yeah, I think that's pretty straightforward. We are just going to have a function that computes us the graph, build graph, and we're going to have a function that explores the component, explore component and we're going to give it a node. We can call this n, that's fine. And yeah, and then all we need to do is we need to build the graph, right? And then we need to iterate over all of our nodes for n in range. I'm reusing the variable here in n, right? And we're just going to explore component that starts, we're going to explore the component that is to which n the node n belongs. Explore, maybe we should call this num nodes instead. Maybe we should choose nodes, or I don't know, I don't like the name. Yeah, maybe we should call this M. Not decided yet. Anyway, let's just reuse it. Explore component, and well, every time we explore a component, we have to increase our result. And in the end, we're going to return our result. We also have to initialize our result. In the beginning, we have 0 connected components, right? But we also need to be careful not to visit components again. So we have a visited set, and we're going to check if n in visited. We're going to skip over that because that means that node was already part of a component that we explored or that we visited. And otherwise, we're going to just explore the component from there. We're also going to pass in, well, if we go with a recursive, yeah, let's go for a recursive approach. Component. So we're just going to explore the component from there. And then finally, we're going to update our visited, update with the components, with the nodes that we visited. Components. So in our explore components method, we'll have a little visited for ourselves. That is a set. And we should probably pass it in so that we can use this in a recursive call. Visited, right. And in the end, we're going to return visited for component. Maybe we should call this component. Yeah, we will return the component. And when we explore it, well, in the beginning, the component is empty, so it's an empty set. So we pass that in, right? So visited is that, and this. If n, maybe we should say not in visited. Then we do that. Then we explore the component, update our visited, and increase the component counter by 1, which is result. Cool. So yeah, what should we do first? Explore the component or build the graph? Well, let's build the graph first. So we'll have a graph that we need to build. And we know how many elements we have. Maximum is n. So we're going to put in a node for node in range n, right? I really don't like this, so I'm just going to call this num nodes. Num nodes, in range num nodes. Then we can use n for node if we wanted to. Actually, no, let's not rename this to. Let's just do this. For node in range n. And we just call it node. Why not? Why was I so fixated on reusing n? I don't understand anymore. Cool. All right, so iterating over all of the nodes. If it's not in visited, well, we're going to explore it, and we just need to make sure that we're going to add it to visited. So if node in component, there's nothing to do. Sorry, node. But if it's not in component, there is stuff to do, right? And so what we'll do now is, well, we get the neighbors. And I just realized we also need to pass in the graph. Otherwise, we don't know how to navigate through the graph. So what we'll do is for child in, or neighbor, you could call neighbor in graph node, and we're just going to explore it. We're just going to explore it. Explorer component graph neighbor component. It's that easy. That easy. Except for we have to perform a check as well, right? We actually have to add the current node to component. Add node so that we don't visit that one again. Otherwise, we would end up in an infinite loop in our recursion here. So yeah, that is the recursive approach. And then in the end, we return all the nodes that belong to that component. And we're going to update our visited set so that we don't try to revisit any of the nodes that were part of the previous components. I have explained this many times before. So now the only thing that is missing is building the graph. So the first thing we do is we ensure that all nodes are in the graph, even if they're not listed in our edges. Next is we iterate over all of edges, in edges. And what did they say was dependency? Well, it went into both ways, right? Because it's an undirected graph. So actually, now what we have to do, we have to add both edges in both directions to our graph. So graph from the source, append destination, and the other direction as well, append src. And then finally, we just return the graph, return G, the graph. Cool. So it's really important that we add all of the nodes. Otherwise, you know, we're only traversing nodes that, let me think about this again. You are given an integer n, an array, blah, 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 indicates that the edge is between, yeah. If we have isolated nodes, for example, if we have like a node here, and we have a component here and whatever, this one doesn't have an entry in the edges array because there's no edge to it or from it. So if we only build our graph from the edges, that means we're not even including this one, right? So we will never be able to count this as an individual component of one node. That's why it is important to put all of the nodes, even if they don't have any connection, into our grid. So actually, and I see an error here, so we have to add an empty list. And yeah. Cool. Space and time complexity. Well, we need to visit all nodes and all edges. With graph problems, if you need to visit everything, it's always number of vertices plus number of edges. And we're not going to revisit anything, so it just stays that. Time and also space. Right. And time and space is because we're building this graph structure again. Right. That's why. And we're also doing a recursion. So our recursion can be as deep as we have number of edges or number of nodes in the worst case when the graph is like a linked list. So that is, yeah. Let's test this. Let's see if I missed any typos. Okay, components is not defined. Components. I wrote components there, typo. Right. Nice. So that worked out. And yeah, let's do the big submit to see if that passes. And it passes. Congratulations. So yeah, that concludes this problem. Like I said, it's very similar to the number of islands problem. And yeah, that concludes this video.